Good morning, everyone. It's 10 a.m. here in France, and it's time to start this first training session of the um, the, the series of trainings, web training webinars uh, for the project RESQTOOL. I am Bruno Vicenzi from the European Powder Metallurgy Association. I'm the coordinator of the dissemination and communication for this project, and it's my pleasure to guest to host you today. I will have three speakers to present today. The first one will be Kenan, the coordinator of the project, who will be speaking in a few seconds. And then we will have the two actual lessons or lectures, how do you want to call them? One from Teemu KARHUMAA from GTP Finland OI, and the second one from Angela SERPE from the University of Cagliari, both partners of the RESQTOOL project. So we have 1 hour and a half ahead of us, and we hope that you will enjoy this session, that we will learn something interesting, and be more motivated to follow our project in the next activities and in our events, and finally understand our results. So now I will call to the stage the first speaker. This is, as I mentioned, my colleague Kenan, who is actually sitting just beside me and now will come on stage. Kenan, if you can switch on. Yeah, there you are. Just speak so that we know it's working.
Yes, do you hear me?
Yes, perfectly. Okay, great. So I will leave the room to him now, and I will switch back to this situation where you can see the slides. So, okay, Kenan, the floor is yours. Let's see what the RESQTOOL project is.
It's okay. Do you see the screen?
Yes, perfect.
Okay, thank you. Hello, everyone. My name is Kenan. As Bruno mentioned, um, I'm one of the technical managers in EPMA. Together with Bruno, we are managing RESQTOOL project, which is a very important project on recycling of hard metals. Today, we will have two important presentations from our two main paths of recycling. One is zinc reclaim method to be presented by Teemu KARHUMAA, and the other one is biochemical recycling, which is kind of green recycling as well, by Angela SERPE. But before that, I would like to give a couple of words within my slides about the project Rationale and some other topics important for the project on sorting and classification that we are working on. So let's start. Yeah, what the motivation of the project is mainly coming from the Critical Raw Materials Act and the EIT Raw Materials Report. Let's start with the latter one, the EIT Raw Materials Report, which is published in 2024. It basically says that the EU is heavily dependent on critical and strategic raw materials. The European automotive, machinery, and energy technology manufacturers rely mostly on rare earth elements, and the aerospace and defense sector needs imports from CRMs as well for high performance applications. And indeed, that's the last one is an interesting finding that I wanted to put here. The raw materials industries in Europe will need about 1.2 million new workers by 2030, within just 5 years, to meet the demand for skilled labor in sustainable mining, material science, and recycling technologies. So the Critical Raw Materials Act, which is more or less the basis of our project, or the reason why the project has been funded by the European Commission. So for those who doesn't know the Critical Raw Materials Act, it's one of the most important policies of the EU, published in 23. You can find it online available and download it. What it says is basically there are some targets on the extraction, processing, and recycling of critical raw materials act to increase the domestic capacity, such as 10% for extraction, that includes mining mainly, 40% for processing, where Europe is really strong in that, and 25% for the consumption, that is the end users, such as aerospace and others. And also a diversification in sourcing of critical raw materials out of the EU, not to be exceeding 65% from a single third country. On the right side, you see the critical raw materials that are in the scope of this project. That is mainly tungsten, cobalt, as well as it includes scandium, niobium, and tantalum that we are looking after. So, what is the motivation for a project? The third reason is a need for digitalization, that is product coding. The EU regulations on waste management for collection and transportation of hard metal scrap is really complicated, especially in Nordic countries such as Germany, Sweden, Norway, Finland. So we are working on identifying hard metal scrap as a valuable secondary raw material among other scraps in the metal industry. So for that reason, actually, the cutting tool producers in Europe have already started coding these products. As you can see on the right side, there are certain companies that have certain codes, mainly data matrix is used for that. And the good news is that already two of our partners in the project, that is Sandvik, mainly Seco, and Ceratizit, have announced their new products in the markets made by recycled powder, and indeed coded using product passports. So coming to our project, has a global objective of offering a sustainable and energy efficient solution for recycling and supply of critical raw materials, mainly tungsten, cobalt. But of course, we're working on, as I said, tantalum, titanium, and niobium as well. From end-of-life products, that is what we call as hard metal scrap, but actually we don't want to call it scrap anymore, as we consider it as a secondary source of raw material. These end-of-life products come from cutting tools, construction, manufacturing devices such as drilling bits, etc. And we are trying to develop certain recycling processes by lowering the carbon footprint and developing advanced technologies for those. We have 12 participants for the project, the coordinators, the EPMA, and the total budget is 8.8 million euros, funded by the EU. The project started in July 23 with a duration of 4 years. Now you see on the geographical map our partners. As you can see, most of the important European hard metal producers are in the project, as well as some other partners for developing sorting and separation technologies. And also we have important universities and research centers for characterization, validation, and functionality assessment, as well as the sustainability side taken care by IMR in Ireland. So as of today, this is our current value chain of hard metals, starting by the product design and the supply of raw material, where tungsten is mainly coming from China, cobalt is coming from Congo. We make the tool production in Europe, and they are used in automotive, mining, metal, wood cutting, and other industries. And in the end, these scrap are collected, and unfortunately, as of today, there's a kind of downcycling, which as a project we are trying to avoid this. What we mean by downcycling is either alloying of tool steels, these where the hard metal scrap is used, or hard facing for reuse, let's say. So what we are trying to do in the project, as you can see in the chart, we are trying to develop a circular business model where the product is end-of-life products are collected, they are sorted and classified, as I said, using certain coding systems, and then they are recycled back to the powder stage, and this material supply is used in tool production. So how we do it, as I said, we first identify the scrap sources by their users in the industry, and we have assigned a certain recycling code for each group to be used there to determine their recycling scheme. And we also have investigated samples that we have collected by their size and shape, composition, origin, mass, to develop the proper coding in terms of recycling and as well as other projects. As I said, these codes are used for product identification mainly, but we want to include recycling detail there as well. So this is the methodology of the project. As I said, we have defined our main framework of data where we get the hard metal scrap, and then the methods of sorting and classification, and then we have the recycling technologies development. That is, of course, all the time followed by characterization of the powder and the assessment of the final products coming from real case studies in our consortium partners. And of course, all this is evaluated under sustainability aspect using LCA methods and eco design. So as I said, basically today we will have two important presentations on two different recycling methods. But before that, I would like to give you a short description about the sorting and classification, which is very important as well. As I said, we have collected samples from different countries, 13 different countries around EU, and then we sorted them to figure out the sizes, the shapes, etc. And then we use different methods like magnetic separation, sieving, etc., even manual sorting to understand. We used XRF devices for uncoated and large sized materials, and we try to determine the recycling, which recycling method is good for each category, let's say. As I said, in the project, we are mainly working on developing a coding system to be used for hard metal products, and even the EPMA is leading a proposal for a standard in ISO level for that. And as the consortium, we are working on GS1 data matrix standard. We have two main geometries of data matrix. One is the square one is the rectangular one. Square one is rather used for flat surfaces like the cutting inserts. The rectangular one is used for rather rounded surfaces like the drilling bits and milling edges, milling tools, etc. As I said, our goal is to have a product coding that is a kind of product passport for each product, each unique with their own unique ID in terms of traceability and recycling. So finally, I think, or maybe I can have some slides, but basically this is the automated sorting unit we have developed within the project. As you can see, it detects the code, data matrix code, and it depending on its chemical composition or coating, etc., it separates into different classes where afterwards they are forwarded to certain recycling schemes. So we have reached, this is the old news. I mean, this slide was prepared 6 months ago, maybe, so I have to update it. The unit has reached now 97% accuracy, and our goal is to reach not 100 but 99.9 accuracy, so that during the sorting there is no mistake that let's say a cutting tool is not put into the box of milling tools, let's say. So that's all from my side. Thank you very much. I would like to answer your questions at the end of the session, but now I would like to give the floor back to Bruno, because we have two important speakers after me. Thank you.
Well, yeah, actually, if there is any quick question now, we could even take it. But otherwise, there will be time at the end, of course, yes. I don't see anything in the chat. If anyone wants to speak, I will switch briefly to the discussion mode, so you might be able to switch on your microphone and camera if you want. Otherwise, of course, we will move to the next speakers. I don't see any questions yet.
Okay,
so
maybe
there will be more questions on the technical side, I guess.
Yeah,
yes,
probably.
Right. So thanks then, Kenan. It's time to move to our first technical lecture today, and it will be given by Teemu KARHUMAA. Teemu, can you switch on your, yes, there you are. And you will be also sharing your slides now. Yeah, that's coming. Since some seconds to wait for the IT to keep up the pace with the innovation. And yes, there's the slides. So I leave the floor to you, Teemu, and yeah, you have half an hour or so, something like that. Thank you. See you later.
Thank you, Bruno. Hello, everybody. Good morning, good afternoon, depending where you come from. My name is Teemu KARHUMAA. I am head of R&D at GTP Finland, based in Jyväskylä, Finland, as the name says. The company name was changed from Ticomet to GTP Finland only like 6 months ago, and you might have recognized name Ticomet in the Kenan's slides just a couple of minutes ago, but that's why you might have wondered why there are a couple of names relating to the zinc processing. So I would like to give you about half an hour lecture on recycling of hard metals and some results from the RESQTOOL project, which we have reached during our 2 years time, which is the current status of the project. So we started 2 years ago, and we have still 2 more years to go. I would like to start with a very, very short introduction to hard metals. If there is somebody who is not that familiar with tungsten, carbide, cobalt composite materials, then describe you shortly 3 different tungsten carbide or hard metal recycling processes, and then go more details into the zinc processing first, a little bit about the history, and then science, what is the behind this zinc processing, how does this magic happens. And then towards the end of the presentation, I like to give you a review of health and safety aspects of hard metal recycling, especially in regards to cobalt exposure. And then last but not least, some words about energy consumption of the hard metal production and hard metal recycling, and what we have done there within the project. And then I would like to close my presentation with conclusions. So let's go. So as most of you for sure know, hard metal consists of tungsten carbide and cobalt matrix. Tungsten carbide being the hard phase, kind of ceramic material which is bonded together with a metallic cobalt, and the tungsten carbide gives the hardness and wear resistance for the material, and cobalt giving the toughness and small amount of plastic behavior as it has. And there are large variety of applications where tungsten carbide cobalt materials are used. Cold forming tools, wire drawing dies, metal cutting tools in form of inserts or drills and end mills, and then tools for wood working tools, concrete drills, and then stone drilling in the mining area where holes for blasting, for example, is needed, and then also some tools in the gas exploration in the energy energy industries. And on the right side, you see a typical picture of hard metal microstructure consisting of these light gray particles of tungsten carbides, and then in this case black phase, which is the cobalt binder in between of the grays. And as you know, the hard metal tools and parts are produced via powder metallurgical methods. So raw materials are in this case all in powder form, tungsten carbide and cobalt, but then also other carbides or even other binder phases can be used. The materials are mixed and milled typically in a treater or ball mill. The powders are granulated so that they are free-flowing powders, and after that there is typically a quality control step where microstructure, carbon balance, flowability, etc. measures are controlled. The powders are compacted with various methods, and then there might be after compaction a step of green machining if let's say cold isostatic pressing was used to press larger blocks, and out of the blocks some kind of shapes which could not be pressed directly are formed. And then after sintering, the hard metal gets its actual properties, having the hardness and porosity, transfer rupture strength, and etc. And then there can be at the end of the process some post-treatment methods. The parts can be grinded to reach the final dimensions. The parts can be coated typically with CVD or PVD methods, and they can be joined to different kind of other materials like steel structures by welding or brazing, or to some other materials. Tungsten recycling market, as Kenan described, is extremely important for European Union because Chinese mining companies control the majority of the tungsten production in the globe, and yes, there is already existing recycling methods. So about 35% of global tungsten streams comes from recycling already at the moment, and about 65% of all tungsten produced globally goes for tungsten carbide products, so hard metals. So recycling of hard metals is indeed very important to reduce the dependency on of imported tungsten in the EU. And as Kenan described, we try to develop a standard for marking of tools so that they could be better recycled. And in this case, we see that the losses that are currently taking place here on the right side. I hope you see my pointer. A high amount of tungsten goes to losses. That means the parts where they are thrown into garbage, or just discarded. And this share of losses needs to be reduced so that more and more materials can be recovered and recycled. Hard metal scrap can have different shapes and forms and geometries. In this case, we have here, just as an example, some metal cutting inserts or cold forming tools, mixed scrap from any kind of applications, drills and end mills, mining buttons, or blocks from EDM machining. And currently, the sorting of hard metal scrap is done manually based on the application. So the human or the person who is doing the sorting recognizes this is indeed a metal cutting insert, or this is drills and end mills. They put them to the different categories. But if there is no application known, then all this material goes to mixed scrap, and this share we need to improve. So by marking the tools, we can recognize what is the hard metal grade composition, tungsten carbide grain size behind, and these scrap grades can be better recycled in the future. There are also hard metal scraps or tungsten containing scraps in the market, which are called as a soft scrap. So they can be turnings from machining of tungsten containing materials, then sludges from grinding of hard metal drills and end mills, for example, or any kind of powders which were generated during the production of hard metal parts, for example. And all these scrap or secondary raw materials, as Kenan mentioned, can be recycled via several methods. And I here try to describe you in my lecture 3 different methods. But if we look at the big picture of hard metal tools and how the hard metal recycling value chain looks like, everything starts, of course, with tool design. So it's actually a very important phase where many characteristics how the hard metal can be recycled afterwards is defined already. But after using of the hard metal tools, they come end of life and can be either reused directly, like grinded and coated again. They can be crushed, material goes to hard facing, or then they can be leached. So solid hard metal tools can be leached. So the material then which was leached away goes to chemicals, different kind of chemicals, and the remaining tungsten carbide goes to tool production again. And then zinc processing is just a crushing and grinding process, which I will describe you later. And then via chemical recycling, all kind of hard metal or tungsten containing tools can be recycled. And these 3 methods here, leaching, zinc processing, and chemical recycling, I would like to tell you a little bit more in details. But just to keep in mind that there are different environmental indicators for all these recycling methods. And we studied for Planche seminar 2022, so already before the RESQTOOL project, we studied the CO2 emissions from different recycling methods, and we learned that this zinc processing with green electricity is indeed very environmentally friendly in terms of CO2 emissions, and this factor we try to utilize. But on the other hand, under the RESQTOOL project, we try to evaluate with the colleagues from IMR the CO2 emissions from the process more in details. So then these 3 recycling processes, which I like to describe a little bit more in details. Leaching of sintered hard metal scrap. The cobalt binder of the hard metal scrap can be removed. We are using a strong acids, and after leaching of the binder, the remaining tungsten carbide mass or powder can be used for the production of new tools. In the leaching of sintered scrap, there are some challenges because the leaching time can be very long due to the long diffusion lengths, and also the tungsten carbide grains may oxidize. Coatings may create some diffusion barriers as well, and if there are let's say nickel binders or chromium molybdenum in the binder as a grain growth inhibitor, they may complicate the required chemistry even further. Then zinc processing, as I already said, is more or less crushing and grinding process. So zinc just makes it easier to crush the sintered hard metal parts. So there is nothing more than making the sintered scrap back to the powder form. So you see here how the scrap looks before and after the zinc processing, and then how it's in powder form after the processing. But I will describe you a little bit more details about how that happens in a couple of minutes. Then the full chemical recycling method, which is normally utilized, or which owns the majority of the market share in the hard metal recycling market. The tungsten carbide and cobalt and other elements are oxidized and dissolved into sodium hydroxide, and then there is complicated steps of solvent purification and filtrations, and then once ammonium paratungstate is then the outcome from the hydrometallurgical processes. This is then calcined to tungsten oxide. Then tungsten oxide is reduced to tungsten powder, and this is then carburized to tungsten carbide powder. And as you can imagine, already with 3 different pyrometallurgical steps, and then many hydrometallurgical steps before that, the energy consumption of the chemical recycling is indeed very high. But it's only method to recycle, more or less only method to recycle soft scraps and sludges, or very contaminated tungsten-based secondary raw materials. But on the other hand, the quality after chemical recycling is same as from the virgin raw materials, so high quality and high purity materials can be achieved. Then I would like to touch a little bit on the zinc processing history. Zinc process, the earliest patent on the zinc processing or publication in zinc processing comes from year 1944, where there was a company in UK describing how hard metal scrap, when hard metal scrap and zinc was put in an oven together, there was a zinc cobalt alloy formed, and then they described how this alloy of zinc and cobalt can be dissolved with sulfuric acid, and the remaining tungsten carbide can be recovered and used in the production of new tools. This process was not utilized in very large scale, only after Paul Bernard in 1971 patented process continuation for this. So the distillation of the zinc instead of leaching improved the process a lot, and then that process then started to gain market share. And there are typically two different furnace types used in the zinc processing industry. A bell type, like you see in the picture above, and two-chamber design, which you see on the lower right corner. And these two furnace types are utilized currently. And this process was more or less designed and developed in the US by two companies, Metallurgical Industries and Washang Teledyne in Huntsville, USA. And one furnace from Metallurgical Industries came to Belgium, to Coldstream, later Höganäs. And then once Höganäs decided to discontinue the hard metal recycling in Belgium, they sold two second-hand furnaces to a powder customer in Finland, which was at that time named Tekomet. So that's why we are working with zinc processing here at GTP Finland. Tekomet was founded in 1994 for production of hard metal pins for winter tire studs, which you see here on the right pictures. And the raw material was in the beginning acquired from Höganäs in Belgium, so zinc recycled powders. But then 1995, the production of hard metal powder via zinc processing started with one furnace, and then we have increased the capacity since then, step by step. Zinc processing is very simple. So we crush the hard metal parts to powder form with the help of zinc. So when hard metal parts containing tungsten carbide and cobalt is immersed into molten zinc, the zinc reacts with the cobalt binder. As you can see here, this on the left side, you see the typical microstructure of tungsten carbide and cobalt. When this part is put into contact with molten zinc, the zinc and cobalt alloy forms in between of the tungsten carbide grains, and this alloying distracts the tungsten carbide grains further from each other and creates space. And once the temperature is increased and pressure is decreased, zinc starts to boil and is evaporated, and the evaporation of the zinc from this alloy creates then empty space, like seen here in the right picture. And that means that the part has a lot of porosity and is very fragile, can be easily ground to powder form after cooling of the furnace. If you look at the how is the zinc cobalt phase diagram looks like, and when I think about the temperatures where we stay with the zinc processing, and if we think about when there is a hard metal with the cobalt, and the cobalt starts to react with the zinc phase or the zinc alloy, we start moving from the pure cobalt alloy towards the middle of the phase diagram, and when we reach roughly middle, so having half zinc, half cobalt, we get to the alloys which have indeed the higher volume, and that increases the volume of the part itself and makes the matching of the zinc processing. We can also have phases in the structure which have higher amount of zinc, and on the other hand, we know that there is also dissolution of the cobalt from the hard metal parts into the molten zinc. So then in this case, we start moving from this part of the diagram towards the center. So we have multiple phases at the same time existing in the reacted material. And typically the parts look like this on the left side. There is a lamella structure, and these lamellas consists of tungsten carbide rich lamellas, and then zinc cobalt rich lamellas. And as you see here, even though we have here, for example, example here in the middle, the zinc cobalt rich lamella. There are different phases consisting of different amounts of cobalt and zinc. But indeed, the zinc and cobalt both are in between of these tungsten carbide grains. And if we go back once again, then after this reaction has happened, as I described earlier, there is an evaporation step in this during the zinc processing, and zinc is evaporated, and then after evaporation also recovered. So the zinc that was used for the process is used again and again. So only small amount of zinc is lost and needs to be then replaced. Then I would like to come to a health and safety aspects of hard metal recycling. In the EU, there has not been so far a common occupational exposure limit for cobalt. Cobalt has been classified as a hazardous material, but there is no harmonized occupational exposure limit so far. But Committee for Risk Assessment in the EU has recommended to set a standardized or exposure limit, and their recommendation 2022 was that it should be 0.5 micrograms of cobalt per cubic meter for respirable fraction and 1 microgram for inhalable fraction. Then there has been some discussions with the producers what the actual limit should be, and the Cobalt Institute recommended 20 micrograms for inhalable fraction and 5 micrograms for respirable fraction. And then very recently, July this year, European Commission proposed 2.5 micrograms for respirable fraction and 10 micrograms for inhalable fraction. And then there is 6 years of transitional period with a little bit higher exposure limits. But this is now discussed in the European Parliament and the Council. But most probably we will see quite dramatic decrease in the exposure limits for the cobalt dust. And this is one concern for the tungsten carbide or hard metal recycling industry, which we need to take into consideration. And in the RESQTOOL project, we have indeed carried out studies how we could reduce this cobalt exposure in our facility. First of all, we have carried out some modeling. How does hard metal dust behave in the air when there is a dust leak in the production? How far and how the dust behaves together with the ventilation airstreams. And then we have carried out, or we have acquired, a continuous device to measure the dust levels in the production areas. And first of all, if we look at the modeling results, we took some samples from different locations in the production, and we were surprised how high tungsten carbide content is in these dust samples, that the composition corresponds very close to the composition of our powder, and the particle size is also close to the particle size of our powder produced. And then we carried out computational modeling, how we measured all the airstreams coming in and leaving out from a production facility, and checked how that dust would spread with the airstreams. And we were surprised how high in the production facility the dust can go and how long it can stay in the air. And now we are thinking about measures how we could prevent the clean and dirty airs to be mixed, so that we could keep some areas more clean where the employees stay, and remove the dirty air at some other areas. We have measured the dust concentrations in various places in the production facility, and indeed there are some peaks, not very high, but still we recognize there are differences in the dust concentration. Let's say some days can be very good, the concentration can be very low, but some days the concentration can be very high, and we need to find out what are the reasons for these dust leaks. Then last point which I would like to a little bit discuss is the energy consumption of the hard metal production and in the recycling. There are some studies where hard metal production of 1 kilo of hard metal production, sintered hard metal production from different raw materials, and what is the cumulative energy demand of these 1 kilo of sintered hard metal. And we can see that if the parts are made from virgin raw materials, the energy demand can be as high as 430 megajoules per kilo of sintered material. If there is chemical recycling involved, the energy demand already decreases a lot. But if the parts are made out of 100% zinc recycling raw materials, the energy demand decreases even further. But still, the energy demand is very high compared to other materials. And of course, this has to be taken into account when we think about CO2 emissions of hard metal production in general, and also the factor of carbon intensity of the electricity production. Here is one map from 2024. What was the CO2 emission or intensity of electricity production in various countries, and we can see that there is actually very big spread within the EU. In some countries like Sweden and Norway, and also France, where the carbon intensity of the electricity production is very, very low, but then there are other countries where the situation is not that good. And of course, this has to be taken into account when we think about how we can make the hard metal production more sustainable. In the RESQTOOL project, what we have studied is to utilize how we could utilize the waste energy streams from the zinc processing furnaces. So zinc processing furnaces are cooled with cooling water. So they have chamber furnaces which have double walls with the cooling water between. And currently the waste energy is mainly vented outside, so it's waste more or less. And we have studied if we could increase the temperature of the waste heat so high that this waste heat could be pumped to the district heating network. So that would require a rather large heat pump facility to increase the temperature of the furnace cooling water to around 100 degrees C, which then could make it possible to pump the energy to the district heating network, and then the neighbors and the area around us could utilize this energy. But unfortunately, so far the calculations show that the district heating network owner pays very little for such a energy, and we are currently concentrating on this side of the graph. So we try to utilize and planning how to utilize the maximum amount of generated waste heat to heat the buildings, production facilities we have, and more or less get rid of the district heating, which is currently bought to heat the buildings. So let me come to conclusions of my presentation. We believe that the recycling of hard metals and tungsten will increase in the future from the environmental reasons, especially CO2 emissions, because of, we all know that the global warming really is taking place and we need to tackle that. But then on the other hand, due to strategic reasons, as that was mentioned already earlier, Europe is very, very dependent on imported tungsten, and we need to make European Union more independent in that regards. But on the other hand, we believe that there are also economical benefits from the recycling. So utilizing recycled streams or secondary raw materials, hard metal producers can gain some savings as well. And we just need to develop the recycling processes further, not only the zinc processing, but also the chemical recycling processes, which will be then described in the next presentation by Angela. But the most important point is to recover and collect all the scraps from the market to be able to recycle more materials, because currently the recycling market share the growth is limited due to the lack of suitable raw materials. So by marking of the tools, we can, let's say, create opportunities for direct recycling processes, but on the other hand, we still have too much losses of the materials from the supply chain. And with that, I would like to thank you for your attention, and I guess we will have time for questions then after Angela's presentation. Thank you for your attention.
Thank you, Teemu. Well, actually, if there is at least one question here, so we could take maybe one or two questions now, and maybe have some more at the end. Let me switch to the discussion mode so that in case they can also pose the questions directly. I have a comment. I think what last thing you said was interesting. Clearly, we need to improve as much as possible the possibility of recycling, and then of course all the rest comes with that. We know that it's really complicated to sometimes to obtain the waste, which we think is not a waste. I've just read about the Resource EU, say, idea that has been just made public a couple of days ago. That contains also some hints to a possible green listing of waste streams, and I think that could be a solution if we could make that, let's say, implemented for our metal tools, our metal parts.
Yeah.
Right. We have here a question from Mariam. I will read it from a chat. She says, thank you for a nice talk. From a process optimization point of view, which factors determine the success of a zinc recycling batch? What are the desired characteristics of the dezinced material?
Yeah, the efficiency of the process depends on multiple factors. First of all, as the zinc reacts from the surface of the hard metal scrap part, the diffusion of the zinc towards the center of the part gets slower and slower when the reaction rate goes further. So I would say the diffusion depth is typically something like 5 to 10 millimeters. So if we have very large scrap parts, they have to be recycled or zinc processed multiple times. So there is a certain depth of reaction. Then after the furnace process, the reacted powder or reacted material is crushed and ground to powder, and the remaining ore of non-reacted part goes back to the processing. And depending on the cobalt content, tungsten carbide grain size, then the temperature, dwell time, etc. in the process, they define what is the actual yield for a certain hard metal grade. But if we think about the characteristics of the powder after the zinc processing, of course, the zinc residue that is following the powder has to be as low as possible. We are typically talking about a couple of tenths of ppms. But we also know that there are factors which affect the chemical purity of the powder itself. So we are actually also studying in the RESQTOOL project also the effects, what happens if there is more zinc residue in the powder, but the powder has to be almost without any zinc after the processing, and then also fine in the particle size or in the powder morphology, so that it can be easily used in the ready-to-press powder production when together with virgin raw materials.
Right. So I don't see other questions now from the audience. So maybe we will leave them for the last few minutes if we have some more questions for you. Thanks again, Teemu. And then we can now move to Angela, our next speaker, Angela SERPE from the University of Cagliari. I asked her to come on stage. There she is. Hello, Angela. She will talk about more chemical methods and also bio-based. So that's, I think, interesting for everyone. I will switch back to the normal conditions so you can now share your slides and we can have your presentation. Yeah, they're coming. Yes, they are. So Angela, the floor is yours.
Thank you, Bruno. Thank you to Kenan and Teemu for the great introduction to the topic. The work I will present today is being carried out in the group of chemistry and environmental engineering from the Department of Civil Environmental Engineering and Architecture of the University of Cagliari, in very close collaboration with ONCD Tech Hub, formerly named FIMS, and is addressed to share with you the knowledge about new chemical pathways based on the use of biodegradable chemicals to boost critical metals recycling in our metal chain. So, as you know, our metals have a variety of different applications. So they may include the mechanical industries, oil and gas and mining, construction, textiles, etc. And of course, as also Kenan anticipated, tungsten and cobalt, that are the main components of our metals, are both critical and strategic raw materials for European Union, but also globally speaking. So waste represents the best resources today for facing the problem of the supply of these materials. Teemu already spoke about the possible recycling methods of tungsten and cobalt from hard metal waste. I will just spend few words just to focus on the importance of the chemical approach to the recycling, taking into account the possibility that chemical leaching and recovery may add to the also the direct recovery methods. Indeed, the zinc process is part of the so-called direct methods that are addressed to obtain hard metal powders that can be reused for hard metal manufacturing purposes. The goal, the approach is to form voluminous and brittle phases that can be grinded and then providing a new powder that contain the same amount of cobalt and tungsten that the former material, the starting material. So the pros is that this kind of processes are not involving chemicals in their production, and also do not produce wastewater at the end of the process. Of course, they involve a few steps for obtaining a material that can have properties closer to the ones of the raw materials. On the other side, the main aspect that in some cases hamper the use of these recycled powders is the fact that it's not possible to tune the amount of cobalt and tungsten inside the mixture. So the versatility of the process is lower than the application of chemical approaches. And also the presence of interferences or polluting species inside or on the surface of the pieces can be is difficult to be removed. So on the other side, we have the chemical methods. Teemu already mentioned also this kind of approach. I just wanted to underline that these chemical methods always or often exploit also thermal treatments, and typically provide an intermediate species like tungsten oxide that is treated by using strong alkaline solutions or directly an alkaline melting, so using a large amount of strong bases. Then to obtain the different products, the different semi-finished material for manufacturing purposes, there are several chemical transformation that requires a quite wide amount of strong chemicals. Of course, the main pros is the versatility of the system, also the quality of the recycled materials that can be reused for a variety of applications, like the ones obtained from concentrated from mines. The cons, of course, are the use of a large amount of harmful chemicals and the production of wastewater that should be treated in a certain way, and also accompanied by an higher energy consumption. There is an intermediate process. This is called that Teemu called leaching, is a selective dissolution of cobalt, which is the most reactive in the mixture tungsten carbide cobalt system, and can be dissolved by using, for example, strong inorganic acids. As Teemu anticipated this kind of approach is selective, so we can reuse in a certain extent the tungsten carbide that remain unreacted, but the use of strong acids, in particular the use of strong oxidizing acids like nitric acid or sulfuric acids, often is the make an oxidation on the surface of the material. So this oxidation on the material require a further reduction step, thermal reduction step, to obtain again the tungsten carbide cobalt material with characteristics that are suitable for hard metal production. In the last year, a new attempt has been done by using a weaker acid like organic acid in the presence of an oxidant. Also, in this case, we can observe a selective leaching of cobalt, but the efficiency of these acids, in particular when we work on hard scraps, can be lower with respect to the inorganic acids. So the use of the oxidant is necessary, and the presence of these oxidants, in particular when work in water, may create oxidation and passivation on the surface. So also in this case, there are pros related to, in both cases, selectivity of the action, and cons that are related to the efficiency or oxidation hydration phenomena on the material that require further thermal steps to obtain the desired semi-finished product for manufacturing. Anyway, organic acid demonstrated a peculiar capability to interact with cobalt, but also historically is known that also tungsten in some cases is able to interact with tungsten with the organic acid in specific conditions. So in this review paper, we made an excursus on the different methods, chemical methods adopted during this last century to treat both the raw materials and also the hard metal scraps in order to valorize the tungsten and cobalt present in the mixture. And in particular, in this review, we focus the attention on the use of organic acids on different semi-finished material in order to obtain a more sustainable, if possible, recycling of these critical metals. This kind of approach has been used in the RESQTOOL project, trying to implement low-impact chemical methods for the recovery of critical raw materials from tungsten industrial scraps, in particular based on the use of bio-derived organic acid. The idea is to exploit the peculiar chemical behavior of tungsten and cobalt towards organic acids were present in different oxidation states in the material. The idea is to produce valid recovered material which are flexible as the recycled material obtained by conventional chemical methods for using them in an hard metal industry, increasing the rate of recovered materials with respect to virgin ones in hard metal production. In this study, a selection of organic acids have been made. These organic acids are all easy available, bioderivable and biodegradable, and renewable. And they are all carboxylic acids that show capability of complexing metal species through the carboxylate entity. These acids, or a part of these acids, can also be obtained by biodegradable organic waste through easy transformations. So they have also a source that can be generated directly by, for example, agro-industrial plants or activity. In this slide, I just would like to show you a study we did on the behavior of organic acids toward a metal like cobalt. Because organic acids are, yes, a family of carboxylic acids, and they are less strong acids with respect to the conventional mineral acids. In particular, they are considered weak acids because their pK are lower than 1. So they can behave like acids, but they are not. They have not the same strength like acid towards the different compounds, because they can have different pKa, and then some of them can be considered stronger than others. And through this kind of study, we were able to define two main classes of organic acids, because in the metal oxidation, in the metal leaching from, for example, tungsten carbide cobalt alloys, we need, for making cobalt into solution, we need an oxidizing leaching. So we need the oxidation of cobalt to cobalt 2+, and the formation of a soluble species that can be dissolved in the solvent of the leaching. This is possible mainly by using this kind of acids with respect to the conventional mineral acids, because organic acids contain the carboxylate moiety that is able to coordinate the metal and then stabilize the metal in the complex form that is often a species more soluble in water or in other solvents that can be selected for the leaching. So we need, for this kind of leaching, a double action, the oxidation that for strong acids displayed by H+, providing a hydrogen gas evolution, or should be played by other oxidizing agents if the acid is not strong enough for playing this role. The organic part instead may play as a coordination for the metal. In this table on the right, I can probably no. In this table on the right, you can see how the behavior we observed by reacting cobalt with a selection of organic acids. You can see that in some cases the reaction occurs by the presence of oxygen, and in other cases the reaction doesn't require the presence of oxygen and produce instead hydrogen like a product. In the case we observe the the formation of hydrogen S product, it means that the organic cases is playing the role of oxidant in the reaction. The reaction instead that don't provide hydrogen X product are going ahead through the oxygen consumption. So oxygen dissolved in the mixture is able to oxidize the metal and making it available for coordination. So as you can see in this table, not all the organic cases behave in the same way. For this reason, we made a study into in water solution to highlight the possibility for different acids to play the role of oxidant in the solution or not. And we divided these two classes, calling class 1 and class 2 acids, where acids with a higher pKa and higher capability to coordinate the metal may play the role of oxidizing agents into solution. Instead, acids with a lower an higher pKa, if we are speaking about the minus log of the constant, of course, when we have a lower pKa, we have a stronger acid. So when we have, I can summarize, when we have a lower pKa and a higher K formation for the complex, we have a stronger acid, so a class 1 acid that can behave like an oxidizing agent. When we instead have a higher pKa and a lower Kf, we have a class 2 organic acid that do not behave as main oxidizing agent in the solution. So we need an external oxidant for providing the reaction. In that sense, we can see that citric acid, maleic acid are acids that are able to oxidize the metal. Instead, for example, acetic acid or lactic acid are in the class 2, so needs oxygen for supporting the reaction. Lactic acid and the itaconic acid are at the edge of the two categories, so we can see that the reaction occurs also if oxygen is not still present in the solution, but the efficiency is very, very low. So here you can see the behavior of the two classes of agents. In particular, class 1 is able to dissolve the metal in water, but also class 2, because in water is present a certain amount of oxygen dissolved. Of course, we also observe that the presence of the forced aerating condition may help the efficiency of the reaction. This is important, this classification is important because it means that when we have oxidizing acids, we can work also in solvent different from water. And this is important because the presence of water when leaching tungsten carbide cobalt alloy can promote oxidation phenomena on the surface. So avoiding water can be an option for treating this kind of materials, avoiding oxidation on the surface. So the studies on these different acids and their different behavior on cobalt are reported in this recent article that can be interesting for the ones that are more interested in the deeper chemical aspects. So now we can see the application of this kind of approach to the material, the real material that can be provided, for example, by a regeneration, thermal regeneration process that is able to produce tungsten carbide cobalt powders starting from end-of-life tools. In particular, this regeneration process, in our case, is being carried out by OnCD Tech Hub through a first oxidation step that provides oxidized powders, then a reduction step that provides reduced powders, and a further carburization step that provides the final VCCO powders. If we are able to interact with cobalt and tungsten on the different semi-finished materials that are obtained in this regeneration process, we can be, in principle, be able to tune the composition of the final material, obtaining the desired tungsten carbide cobalt mixture for industrial purposes. So we can apply the leaching by using organic acids on the potentially on the three semi-finished products of this regeneration process, in particular on the POX powders. In that case, we are using the organic acid to leach already oxidized cobalt and tungsten in the mixture. Or, we can treat the reduced powder by using organic acids, for example, avoiding further oxidizing processes on the surface. Then we can treat the last VCCO powders in order to obtain directly the desired composition and send the recovered material to the manufacturing. These three potential addition of organic leaching on the three semi-finished product is called in the RESQTOOL project BioCR, like bio-based chemicals recycling process. So I will show you two examples of application of this kind of system on the two main fractions of this regeneration process, namely the VCCO powders and the POX powders. And just to show you how the material can react differently with organic acids depending on the oxidation state of tungsten and cobalt. And also trying to understand which are the implications on the quality of the material that can be obtained by applying this kind of approach to the different fractions. So here is reported the application of a solvometallurgy leaching by using maleic acid on a already reduce tungsten carbide cobalt powder, where the cobalt is present in 20% in the mixture. And we applied the leaching selectively on the material, trying to reduce the amount of cobalt from 20% to a desired 6% in order to obtain a material specific for certain industrial application. We treat the material inside a 30-liter reactor, double-walled reactor, in the presence of an ethanol solution, 1 molar solution of maleic acid. The reaction was performed at room conditions, so at room temperature and pressure, for 6 hours. In this graph on the right, you can see the XRD pattern of the material before the treatment. So the pink graph, the pink pattern is related to the pristine material, where are visible the two phases, the tungsten carbide and cobalt phases, and instead the green graph report the material after 6-hour leaching, where the cobalt is difficult to be seen in the presence in the pattern. And ICP analysis on the solid material and on the solution agreed to find the 70% of cobalt into the leachate, and so around 6.1% of cobalt in the remaining tungsten carbide cobalt mixture. So, making this selective leaching, we obtain the right composition, but we also needed to assess the quality of the material, trying to assessing the possible oxidation residual on the surface. And as you can see in this table, we make a comparison on the properties of the pristine material and the treated material, and also with a reference 6% cobalt powder obtained by raw materials, and we found that the characteristics of hardness and density and the magnetic properties of the materials obtained by the recycling were completely in line with the ones of the reference material. We found a lower amount of carbon with respect of the desired one. Indeed, the optical microscopy image showed the presence of eta phase, but this is not an avoidable problem that can be also faced by adding carbon in the sintering phase, during the Hardmetal production. On the right side, instead, you can see the results of experiments made for cobalt recycling from the solution, because we were able to isolate the cobalt compounds, the cobalt complex obtained from the reaction of cobalt with maleic acid, that the complex can be isolated at the solid state and then dissolved in water and recover the cobalt like cobalt metal directly on a cobalt cathode. So this is an example of how we can play on the coordination chemistry of the organic cases towards cobalt to promote selective leaching by tungsten carbide cobalt mixtures, avoiding oxidation phenomena in these cases by using solvometallurgy instead of water like the main solvent. And the results are shown in this paper that you can find in the literature if you are interested in more details. And the second approach, the ones that we are studying in the RESQTOOL project, is the treatment of the oxidized powders of the regeneration process by ONCD Tech Hub. And the oxidized powders contain mainly, as you can see in this picture, two phases, tungsten oxide and cobalt tungstate that have a completely different chemistry with respect to tungsten carbide and metallic cobalt. So in this mixture, cobalt react as a lower reactivity towards organic chemistry, organic acids with respect to the reduced powder. Instead, tungsten is more prone to react with organic acid. In these cases, we have made a variety of experiments, and we obtained that by using lactic acid solution in buffer conditions at 4 molar concentration, is possible to dissolve, as you can see in this graph on the right side, both cobalt and tungsten. Also, we can proceed by steps by using renewed solutions for dissolving increasing amount of cobalt and tungsten. So through this process, we were able to dissolve both metals that if we would like just to change the amount of cobalt into the solution, in particular decrease the cobalt amount to the solution, it would not necessary, because tungsten can remain in principle in the solid residue. But it is really interesting when we have other metals in the mixture, because in that case we are able to dissolve both cobalt and tungsten and obtain the selective recovery at the end of both of these metals, avoiding contaminants or metals that are not desired in the mixture. If you see here this image, of course, the organic treatment on the oxidized powders have the benefit that already the thermal treatments are already planned in the regeneration process for obtaining tungsten carbide materials. So the recovered materials underwent leaching was then treated by thermal process for reduction and decarburization, obtaining tungsten carbide cobalt material very, very good in properties, with TRS value good for practical applications. The fact that we can divide the process in different steps made us able to design a predictive model to predict the number of stages that we can apply on the oxidized material to obtain a final tungsten carbide material with a specific composition. Of course, if we leach cobalt and tungsten from oxide material, we then have to recover them from the solution in a selective way. So typically cobalt is recovered from the leaching solution as a carbonate precipitate, adding bicarbonate salts, and instead tungsten oxide can be precipitated in acid environment. So also this part has been published, and you can find more details in this paper. Just for concluding this this presentation, we focused a lot on the behavior of lactic acids because from among the different acids, it behaves really, really well with both cobalt metal and cobalt oxidized and tungsten 6. And so is really, really suitable for practical application. On the other side, we were able also to obtain a mixture rich in lactic acids starting from cheese whey, and the second cheese whey obtained by as a waste from agro-industrial processes. So in this patent, we protect the innovation to obtain a mixture just through one step fermentation, a mixture that has exactly the properties that we need for leaching metals present in several kinds of technological waste. In conclusion, organic acids demonstrate a good efficiency on regenerated powders, both in reduced and oxidized state in mild conditions for the hard metal waste valorization. This kind of green leaching may add versatility to thermal recycling process, and the predictive model allows to systematize the process. They obtain recycled hard metal as a quality accepted by the market, so this is encouraging us to go towards this goal for trying to limit the amount of harsh chemicals in the recycling process. Preliminary but promising results to design eco-friendly alternative to more impacting recycling methods have been obtained and are at the base on the activity of the RESQTOOL project that is addressed to increase the reuse of materials, of secondary materials, and limiting, so in that sense, the recourse to primary sources, and trying to also limit the use of harsh conditions and energy for recycling. So I have concluded this presentation. Thanks for your attention, and I'm open for your questions.
Thank you, Angela. Thank you for your presentation. I hope everyone enjoyed the description of this procedure. We're a bit over time, actually. I can open the discussion, but it should be a very quick one. I don't see actually questions in the chat, so I don't know if there will be more. People can actually open their microphone if they want and speak directly. Otherwise, maybe I can call also the other speakers on stage, and if there are questions for them as well, maybe we can go back also to those. Maybe we could say something, Angela. What is the present capacity of the process equipment that you can access at the moment for carbide cobalt?
Yeah, for the thermal part, of course, the capacity is high because it's already an industrial process. In terms of chemical process, we are working still with a small amount of material. We reached from 1 to 3 kilos of materials each time. But we hope, of course, in the project, the goal is to increase the TRL of the process, going towards a higher amount of material, and exploiting a pilot plant that has been built in FIMS or OMCD Tech Hub. So the goal of the project is right that one, to to try to increase the versatility of the process, and on the other side, higher the TRL of the system.
Right. Right. I see that people are happy, so no questions. Is there any questions also for Teemu or for Kenan? As there were no questions then. I remind you that you can just click on your microphone beside your name and speak directly if you want. No, I don't see anyone. Okay, last chance. Otherwise, I will go. I would say that with about 10 minutes more than expected, we can close this session, I think. I hope you enjoyed the presentation. I thank the speakers again, friends and partners for the RESQTOOL project. And well, we invite you to take part in the second session of this series that will happen in a few months, probably, clearly on another topic with other speakers, and we'll cover more or less the topics of our project, but trying to give also, as you can see, a little bit wider view on not just on our activities, but also the state of the art around. So thanks again, Angela, Teemu, and Kenan, and thank you everyone for being here. We were quite a number, so we are happy for that.
Thank you, Bruno.
Well, yes, thank you. We should be able to publish also the videos quite soon. So if you want to rewatch and maybe take more notes from what has been said, you will be able to do that. Have a nice day, everyone.
Thank you.
Thank you.
Bye. Bye-bye.
Bye.
Bye.